Welcome to the Deep Dive. We take stacks of research, expert analysis, sometimes conflicting sources, and we boil it all down for you. The goal: to get you up to speed on complex topics without you having to wade through everything yourself. Today we're diving into something that honestly still sounds a bit like science fiction, but it's rapidly moving into the realm of engineering. We're talking about the quantum internet. I want you to just imagine for a second an internet that isn't just faster. We always want faster, right? But one that's fundamentally, provably more secure than anything we have today. An internet that could unlock types of computing, types of sensing, things we're only just starting to really grasp. Now, it sounds complex, definitely. Lots of physics involved that can seem, well, intimidating. But our mission here is simple: to make you quantum fluent, or at least conversational. We'll distill the core ideas, the really important bits from all the cutting-edge work happening. We want to equip you with a solid understanding, so you're ready for what's coming in communication, in computing, without getting bogged down in the weeds. We'll explore what it is, sure, but maybe more importantly, why it matters so much. For security, yes, but also for computation, and even for things like super precise timekeeping, or, believe it or not, medical diagnostics.
And that why you mentioned, it's becoming, well, it's not just important anymore, it's getting critically urgent. We are genuinely standing, right now, on the precipice of a huge shift, one that really does pose an existential threat to our current digital world. There's this looming shadow of what we call fault-tolerant quantum computers.
Fault-tolerant, that means they actually work reliably, not just fragile lab experiments.
Exactly. Not just any quantum computer, but machines stable enough, reliable enough to run complex calculations for long periods. That's the goal, the holy grail, really. And that's what makes them a true threat to today's encryption. And what's really worrying, frankly, quite chilling, is this concept called harvest now, decrypt later. This isn't theory, it's happening.
Explain that. What are they harvesting?
Sensitive data, encrypted data being sent right now. Think government secrets, corporate IP, your financial data, your health records. It's being intercepted and stored today by adversaries, state-sponsored groups, you name it. They're essentially stockpiling this encrypted data, banking on the fact that future quantum computers will be able to break the encryption and read it all.
Wow, so decades of secrets suddenly exposed.
Potentially, yes. The entire digital history of a nation, maybe. It creates this immediate strategic need for governments, for businesses, to act now, preemptively. And this deep dive, it's about uncovering how the quantum internet offers a fundamental solution, one built not on mathematical tricks that might be breakable later, but on the actual laws of physics.
Okay, let's ground ourselves first. The classical internet. Our current internet. It's been the engine of the digital age, right? An amazing web of fiber radio waves, sending information as bits, zeros and ones. Data travels in packets routed globally. Security relies mostly on computational encryption, things like RSA, ECC. It's been incredibly successful, incredibly robust in many ways. But like anything, it has vulnerabilities. And it sounds like those vulnerabilities are about to be seriously tested by this quantum future.
Indeed. The fundamental weakness, as you say, is in the security itself. Classical security relies on computational complexity. Basically, mathematical problems like factoring huge numbers, problems that are just too hard for today's best classical computers to solve quickly. Not impossible, just astronomically time-consuming.
Okay, so hard math keeps things safe, for now.
For now. But then quantum computers come along with algorithms like, most famously, Shor's algorithm. These quantum algorithms are specifically designed to efficiently solve those exact hard math problems that underpin RSA ECC.
The very things protecting our banking, our secure communications.
Exactly. Suddenly, those problems aren't computationally hard anymore for a quantum computer. And that reinforces the harvest now, decrypt later threat. It's not hypothetical. Data encrypted today is vulnerable tomorrow. So thinking bigger picture, unless we adapt, a huge amount of sensitive data we rely on today could be compromised down the line. Governments, companies, individuals. You need to understand your current data security probably has an expiration date.
So if the classical internet security is facing this ticking clock, what's the quantum internet's answer? You said it's not a replacement.
That's key. It's not a replacement. Think of it more as a profound evolution. A hybrid model.
Hybrid, meaning they work together.
Yes. It'll operate alongside the classical internet. It actually relies on the existing mature infrastructure for things like control signals, for routing. But then there's a specialized quantum data plane just for handling the delicate quantum information.
So it adds capabilities the current internet just can't provide.
Precisely. And the core difference, the truly fascinating part, is the security. Classical security, as we said, relies on math being hard. Quantum internet security relies on the laws of physics. Quantum mechanics.
Fighting the universe's rules instead of just a math problem.
You got it. It offers, theoretically, an unbreakable level of security. Let's maybe highlight a few key differences to make it clearer. Classical internet. Binary bits, 0 or 1. Quantum qubits, using superposition. Classical uses packets, routing, amplifying signals. Quantum uses entanglement swapping, quantum teleportation. Totally different mechanisms.
In the security aspect.
Critically different. Classical data, you can copy it, intercept it, often without detection. Quantum data. Thanks to the no-cloning theorem and measurement disturbance, any attempt to eavesdrop is inherently detectable.
You can't sneak a peek.
Nope. And finally, repeaters. Classical ones just measure and boost the signal. Quantum repeaters are these complex devices that swap entanglement to preserve the quantum state over distance. These are fundamental shifts, not just upgrades.
Okay, let's really dive into that quantum part. Qubits. Superposition. You said it's not just 0 or 1, but potentially both at once. How is that so different from just a maybe?
Right. It's more subtle than just maybe. A classical bit is definite, on or off, 0 or 1. A qubit leverages superposition. It can be 0, it can be 1, or it can be in a specific combination of both simultaneously. Think of it less like a spinning coin that's neither heads nor tails yet, and maybe more like a wave. This quantum wave holds the potential for all outcomes at once, each with a certain probability before you actually measure it.
So it explores possibilities in parallel.
Exactly. That's where the power comes from. A classical computer with n bits is in one of 10 states. A quantum computer with n bits, it exists in a superposition of all 10 states at the same time.
That's exponential.
It is. It lets them process vast amounts of information simultaneously. But, and this is crucial, there's the measurement problem. The moment you measure a qubit, its superposition collapses.
It has to choose.
It's forced into a definite state, 0 or 1. And the outcome is probabilistic. If it was an equal mix, you've got a 50-50 chance of getting 0 or 1. This collapse, this probabilistic nature, is fundamental to quantum mechanics and how we use qubits.
Okay, now, here's where my brain starts to hurt a bit. Entanglement. You hear about it all the time. Einstein's spooky action at a distance. It sounds impossible.
It feels impossible, counterintuitive, but it's very real. Imagine you create two particles, say photons, together in a special way. Their quantum properties, like spin, become linked. Inextricably. So linked that if you measure the spin of one and find it's up, you instantly know the other one, no matter how far away across the lab or across the galaxy will measure as down. Their fates are perfectly correlated.
Instantly. Faster than light.
That's the common misconception. The correlation is instant, yes.
Yeah.
But you cannot use entanglement to send information faster than light.
Why not? If I measure one, I know the other.
Because the outcome of your measurement on your qubit is random. You can't force your qubit to be up just so your friends is down to send a message. You find out it's up, and then you know your friends is down, but you still needed to communicate classically, like calling them, to compare results or use that correlation.
Okay, so no FTL phone calls. What's the point then?
The power isn't in speed, it's in creating these shared secret correlations between distant points. That shared secret, that perfect correlation guaranteed by physics, is the resource that enables secure communication protocols, distributed computing. It's the fundamental link. Which brings us back to security. How can we be so sure it's truly unbreakable if it sounds this weird?
Yeah, how do we trust it?
Two fundamental laws. First, the no-cloning theorem. It's physically impossible to create a perfect copy of an unknown quantum state.
Meaning an eavesdropper can't just copy the quantum information passing by.
Exactly. Any attempt to copy it will fail, or more likely, disturb the original state. It leaves a trace. You can't photocopy a quantum state without messing it up. Second, Heisenberg's uncertainty principle. Trying to measure certain properties of a qubit inevitably disturbs other properties. So if an eavesdropper tries to measure the information to steal it, the very act of measuring changes it.
Like trying to see something delicate by shining a bright light on it? The light itself changes what you're looking at.
Precisely. Any eavesdropping attempt is immediately detectable by the legitimate users. There's no way to passively listen in without leaving fingerprints all over the quantum state.
So putting that together, what this means for you, thinking about security, we're talking about something fundamentally different from classical encryption, aren't we? It's based on these unavoidable physical laws.
It really is. When we talk about unbreakable in this context, we mean security guaranteed by the laws of physics, not just a hard math problem that maybe someday someone clever or some future computer could crack.
The universe itself enforces the security.
In principle, yes, for perfectly implemented systems. The practical challenges, the asterisks, come from imperfect hardware, engineering flaws, side-channel attacks on the devices, human error. But the quantum protocols themselves, if executed perfectly, are secure against any adversary, even one with a quantum computer. It's a profoundly stronger guarantee than relying on math problems that we merely believe are hard.
That's a critical difference. Okay, so building this thing, you said it's a hybrid model.
Yeah.
How do you actually get the classical internet and this new quantum layer to talk to each other? They seem like completely different languages.
That's where the design gets clever. It's this dual-plane architecture. Think two parallel lanes. One lane, the quantum plane, carries the fragile qubits themselves. Remember, you can't read these in transit without destroying them. But running alongside it, on the classical plane, is a standard data header, like the address label on a package. This header has all the control info, the routing instructions, stuff that can be read and processed by normal network gear.
Ah, so the classical network guides the quantum information without touching it.
Exactly. It allows the whole hybrid system to use the same internet protocol, IP, that runs today's internet. The quantum internet can essentially speak the same language for control and coordination while keeping the quantum payload secure and untouched.
Sounds elegant, but are there catches?
Oh, definitely challenges. Unlike a neat classical packet that sits at one place, a core quantum resource, like an entangled pair, is inherently distributed across two nodes. Managing these distributed states, correcting errors across them, it needs totally new network protocols. And coordinating the classical control signals with the quantum state in memories, ensuring everything happens at the right nanosecond, that adds latency, adds complexity compared to just firing off classical packets.
Okay, so what kind of new hardware, new gadgets does this quantum network actually need? It can't be just routers and switches, right? You need specialized gear. First, you have the quantum nodes. These are basically the endpoints. Think of them as quantum processors or small quantum computers that sit at the edge of the network. They're devices that can actually create, send, receive, and manipulate qubits. People are building these using various technologies, like nitrogen vacancy centers, which are tiny defects in diamonds that act like stable quantum bits.
Or trapped ions, where individual charged atoms are held and controlled very precisely using lasers and electric fields. These nodes are the interfaces between the quantum network and whatever task you're doing, computing, sensing, communicating.
Then you mentioned quantum memories. Why are they so critical?
Memories are crucial for scalability. Think of them as quantum buffers. They have to hold a qubit state without measuring it, preserving its superposition and entanglement.
Why hold it? Why not just send it straight through?
Because entanglement generation, especially over distance, often relies on probabilistic methods. You might succeed in creating entanglement in one segment of a long link, but fail in the next. Without memories, the qubits in the successful segment would just decohere, lose their quantumness while you wait for the other segments to catch up. Memories act like waiting rooms, holding the qubit safely until all parts of the link are ready for the next step, like entanglement swapping.
Which brings us to the quantum repeaters. You said they're the game changers for distance.
Absolutely essential. Quantum signals, usually photons in fiber, fade out very quickly. Photon loss is a huge problem. Classical networks solve this with amplifiers, measure the weak signal, create a strong copy.
But we know you can't measure a copy of qubit.
Exactly. So classical amplifiers are useless. Quantum repeaters are the solution. They work on a kind of divide and conquer strategy. You break a long distance, say London to Paris, into shorter segments, maybe London to a repeater station, repeater to another, then to Paris. The repeaters generate entanglement across each short segment. Then, at the intermediate repeater stations, they perform a special operation called entanglement swapping. This involves a clever measurement, a Bell state measurement, that doesn't reveal the qubit states, but confirms entanglement between qubits from adjacent links. The effect is to stitch the entanglement together.
So you end up with entanglement directly between London and Paris, even though no single photon traveled the whole way.
Precisely. It teleports the entanglement, essentially creating a direct quantum link over the long distance by patching together shorter, more manageable links. It bypasses the distance limitation imposed by photon loss and decoherence. It's incredibly complex, but elegant.
It really is. And these repeaters themselves are evolving, right? Through different generations.
Yes, it's a rapidly developing area. The first generation relies heavily on that probabilistic entanglement generation we mentioned, plus something called entanglement purification.
Purification.
You generate lots of imperfect, low-fidelity entangled pairs. Then, through measurements and classical communication, you basically sacrifice some pairs to distill one higher fidelity pair from the bunch. It works, but it's slow because it's probabilistic and needs that back-and-forth confirmation.
Okay, less than ideal for high speeds. What about the next step?
Second-generation repeaters improve on this. They might still use probabilistic methods to generate entanglement, but they incorporate more deterministic quantum error correction code.
Error correction, like in classical computing.
Similar idea, but quantum. Instead of just purifying noisy pairs, these repeaters actively encode the quantum information across multiple physical qubits. This redundancy protects the information if one qubit is lost or decoheres. It makes the process more robust, more resilient to errors, though it adds hardware complexity.
And the cutting edge, the future.
That's third generation, often called all-photonic repeaters. This is the most ambitious approach. The goal is to get rid of quantum memories altogether, as they're a major bottleneck. Instead, they'd use large, specially prepared states of many entangled photons called cluster states. These states have error correction built in, intrinsically protecting against photon loss as they travel.
Wow. So the error correction happens on the fly.
Potentially, yes. It promises much higher speeds, no memory delays. But the overhead is huge. Creating and managing these complex multi-photon states is incredibly challenging. It really shows the direction the field is pushing, though.
That's incredible progress. Okay, let's shift gears. All this amazing tech, qubits, entanglement, repeaters, you might be sitting there thinking, sounds cool, but what can I actually do with it? What's the so what? Well, the most immediate, most headline-grabbing application is unbelievably secure communication. We're talking security fundamentally different from what we have now, thanks to quantum key distribution, or QKD.
Right. QKD uses quantum principles, like the detectability of eavesdropping, to allow two parties to generate and share a secret encryption key.
And if someone tries to listen in on the quantum channel while they're creating the key,
the laws of physics guarantee they'll disturb the qubits. The disturbance is detected, the key generation is aborted, and the parties know someone was trying to intercept. It's theoretically unbreakable communication at the quantum level.
the holy grail of secure keys.
Which leads directly into a really important strategic debate happening right now. QKD versus PQC post-quantum cryptography.
Okay, break that down. QKD is physics-based security.
Correct. Unbreakable by quantum computers, theoretically. But it requires specialized hardware, single-photon sources, detectors, dedicated fiber lines. It's expensive, complex to deploy widely. Think millions for an enterprise setup.
And PQC.
PQC uses new classical algorithms, advanced mathematical problems designed to be hard even for future quantum computers to solve. The big advantage, it's mostly software. You can deploy it on existing internet infrastructure, much cheaper, much easier to roll out broadly.
So a trade-off. Physics-based perfection versus practical, widespread deployability.
Exactly. Organizations like the U.S. National Security Agency, the NSA, have leaned towards PQC for most applications, seeing QKD as maybe necessary for only the most ultra-sensitive, highest security links. It's a critical choice for governments, for banks, for anyone handling sensitive data. Do you go all in on PQC, invest heavily in QKD for certain things, or try a mix? It's a complex decision with big cost and security implications.
Fascinating strategic dilemma. Okay, beyond unbreakable keys, what else? You mentioned computing, right? Distributed quantum computing, or DQC. This is huge. Building one single, massive, perfect quantum computer is incredibly hard. Qubits don't like talking to lots of other qubits. They lose their quantumness quickly. Error correction is a nightmare at scale.
So DQC offers a different path. It's like how we build classical supercomputers today, not one giant chip, but clusters of powerful processors linked together.
So link smaller quantum computers.
Precisely. Connect multiple, smaller, more manageable quantum processors using those quantum network links we've been talking about. Entanglement allows you to share quantum information and perform operations between these separate modules.
You can run a calculation across multiple machines.
Yes. You can perform quantum logic gates between qubits that are physically in different boxes, using quantum teleportation facilitated by the network. It allows a network of smaller quantum computers to function as one single, larger, more powerful, fully connected quantum computer. Many see this as the most viable route to truly large-scale, fault-tolerant quantum computation.
That really could unlock incredible processing power. But you also mentioned something maybe less flashy but potentially more immediate, sensing.
Yes.
Distributed quantum sensing, DQS, and metrology. This could have huge real-world impact, maybe even sooner than large-scale DQC.
DQS uses entanglement to link multiple sensors together into a single, coherent quantum system. Instead of just averaging noisy data from independent sensors, entanglement allows them to achieve sensitivity far beyond what's possible classically. We're talking measurements at the atomic level with exponentially higher accuracy.
Give us some examples. What could this do?
Okay, timekeeping. Imagine linking the world's best atomic clocks not just with classical signals, but with quantum entanglement. You could create a global time standard so precise it would lose less than a second over the entire age of the universe. Think navigation, fundamental physics,
Wow. Okay, what else?
medical diagnostics. Quantum sensors could potentially boost the sensitivity of MRI scans by maybe 10,000 times. Imagine detecting tumors much earlier, tracking their response to treatment in real time, imaging brain function with stunning clarity.
That's transformative for healthcare.
Or geology and navigation. Quantum gravity sensors could map tiny variations underground, finding mineral deposits, hidden water sources, even tunnels. Quantum magnetometers could do the same. And these sensors could provide incredibly precise navigation where GPS doesn't work, like underwater or indoors.
And you're saying this sensing tech is closer to reality.
Yeah, that's a key point. Commercial quantum sensors are already starting to appear in niche markets. This is important because it strengthens the business case for building the quantum internet now. These sensing applications often don't need the massive quantum computers required for DQC. They provide near-term value, driving investment in the foundational network technologies. It helps build momentum. Okay, the potential is clearly enormous, but let's be realistic. This sounds incredibly difficult to build. What are the biggest roadblocks? The major challenges we still need to overcome? There are definitely significant hurdles. This isn't easy. Probably the biggest one, the one we keep coming back to, is the sheer fragility of quantum states. Right. Qubits are unbelievably sensitive. Decoherence is the enemy. Any tiny interaction with the environment, a stray vibration, a temperature change, a bit of electromagnetic noise, can destroy the delicate quantum superposition or entanglement.
The quantum information just vanishes.
Irreversibly lost. It's like trying to protect a soap bubble in a hurricane. So a huge amount of engineering goes into shielding qubits, cooling them near absolute zero, putting them in vacuums, just to keep them quantum long enough to be useful.
And then there's the distance problem again.
Yes, photon loss. If you're sending qubits as photons through fiber optic cables, they get absorbed or scattered. The signal strength drops exponentially with distance.
And classical amplifiers are no help.
No help at all. They destroy the quantum state. Which is why, as we discussed, those quantum repeaters aren't just helpful, they are an absolute necessity to build a network beyond maybe a few dozen kilometers. Overcoming photon loss while preserving the quantum state is fundamental. Then you have major hardware and infrastructure limitations. We need quantum memories that can store qubits reliably for much longer than they currently can, minutes maybe, not just milliseconds, to allow for complex network operations. We also need to engineer these systems out of the lab, move from room-sized experiments to robust, rack-mountable devices that can handle real-world conditions.
And making different systems talk to each other.
Huge challenge, interoperability. You have labs working on trapped ions, others on superconducting circuits, NV centers, neutral atoms. They all have different ways of working, different protocols. Getting devices based on different technologies from different manufacturers to communicate seamlessly, that requires standardization that's only just beginning. And let's not forget the hybrid integration problem itself. Designing the protocols to manage quantum data alongside classical control signals, coordinating everything perfectly, minimizing latency, it's a massive software and systems engineering challenge on top of the hardware hurdles. Ensuring reliability outside the perfect lab environment is key.
Those are definitely formidable mountains to climb. It sounds almost impossible sometimes. But you mentioned progress is being made. Can you give us a couple of recent highlights, signs that these challenges are being tackled?
Absolutely. The progress is genuinely exciting. For instance, researchers have achieved incredibly high fidelity, like 92% average, in entangling ions with photons, which is crucial for connecting nodes. There was a landmark demonstration in 2021 connecting 3 quantum processor nodes in a network, showing the basic architecture works. Critically for distance, we've seen entanglement distribution and storage demonstrated over tens of kilometers of fiber, like that 22-kilometer link. And loophole-free Bell tests, confirming entanglement over kilometer-scale distances, prove that the fundamental physics holds up outside the lab. More recently, work showing quantum signals sent using standard internet protocols. These are real, tangible steps towards making the hybrid network a reality. The community is chipping away at these problems systematically.
So it's not just theoretical anymore. Okay, shifting focus slightly. This isn't just happening in labs. You mentioned the urgency earlier. This is also a global race, isn't it? With huge geopolitical and economic stakes.
Absolutely. We're talking serious money and strategic positioning. Market projections are in the billions already, maybe $8.1 billion for quantum communication by 2030, growing incredibly fast, over 25% a year. And look at the R&D funding. In 2023 alone, the US, China, Europe collectively poured over $3 billion just into quantum communication research. This is a top national priority for major powers.
And what's really interesting are the divergent strategic approaches. Take China. They have a very centralized state-driven strategy, massive investment, over $15 billion since 2016, aiming explicitly for global leadership. We see the results in high-profile projects like the MISSIS satellite for intercontinental QKD or the Jinan-1 satellite for real-time satellite QKD. It's a very focused, top-down push. It also raises concerns in the West about potential surveillance applications.
How does the U.S. compare?
The United States is different. It's much more driven by the private sector, companies large and small, spurred by government initiatives like the National Quantum Initiative Act, $1.2 billion funding. The emphasis is more on collaboration between government labs, universities, and industry, a more distributed ecosystem.
And Europe?
Europe has a coordinated effort through its quantum flagship program, $1 billion over 10 years, specifically designed to foster collaboration across member states, accelerate breakthroughs, and ensure Europe remains a major player. So you have these distinct models competing. It really is a kind of quantum arms race, not just for scientific bragging rights, but for genuine technological sovereignty, economic advantage, and future intelligence and military capabilities. The stakes are incredibly high.
With such powerful technology emerging, we have to talk about the ethics, the societal impact. With great power comes great responsibilities. Like, what are the big questions we should be asking now before this is widespread? One major concern is definitely the potential for a new kind of digital divide. These quantum systems are incredibly complex, incredibly expensive, need specialist expertise.
Meaning they'll likely be concentrated in wealthy nations and big corporations, at least initially.
Right. And that could really deepen global inequalities. Developing nations might struggle to afford access, leaving them potentially vulnerable from a security perspective and locked out of the economic benefits. We need to think about equitable access, about capacity building internationally from the start.
Absolutely. And closely related are fundamental questions about privacy and individual liberty. We've talked about quantum computers breaking today's encryption. What does that mean for the privacy of all the data we've already generated, our digital history? And looking forward, the potential combination of quantum capabilities with AI raises concerns about highly sophisticated surveillance systems. The risk of data-centric authoritarianism, as some call it, is real. Developing strong ethical guidelines, robust legal frameworks now to govern how this tech is used to protect human rights. That's absolutely crucial. It can't be an afterthought.
These are vital conversations to be having.
Yeah.
Okay, we've covered a lot of ground today. Taking a truly deep dive into this quantum internet concept, it really feels like it's shifting from science fiction to engineering fact. The potential to reshape cybersecurity, computing, sensing, it's immense.
Definitely. To quickly recap the core promises. First, security based on physics itself, a potential answer to the harvest now, decrypt later threat. And second, completely new capabilities through things like distributed quantum computing and ultra-precise quantum sensing. But it's important to manage expectations on the timeline. While some applications like point-to-point QKD are happening now for specific high-security needs, a full-blown, general-purpose global quantum internet is still a long-term vision. It'll likely arrive in stages: regional networks first, specialized links, then broader interconnection.
So wrapping up, what does this mean for you, our listener, looking ahead? One key takeaway seems to be the growing need for what experts call cryptographic agility.
That's the ability for organizations, maybe even individuals eventually, to switch relatively easily from today's encryption methods to the new quantum-resistant ones, whether that's PQC or integrating QKD. Being prepared to transition is key.
The quantum internet isn't some abstract thing happening decades from now. It's being built, piece by complex piece, right now. Understanding its basics, its potential, its challenges, It's becoming essential for anyone involved in technology, security, policy, or, frankly, just living in our increasingly digital world.
And its ultimate success, how it benefits society, really hinges on continued innovation, yes, but also on proactive, collaborative efforts globally addressing the technical challenges, the security implications, and those crucial ethical questions we raised. It starts with awareness, with conversations like this one.